started in Chapter 2, 2-1, Inductive Reasoning and Conjecture. A lot of Chapter 2 is going to be you kind of learning how to use the terminology that you've learned in Chapter 1 and are going to keep learning, and how to apply that to future problems or to predict future values. So that's what we getting into in 2-1. All right, inductive reasoning is basically looking at, and for math, how we use inductive reasoning is looking at a set of numbers or a set of data and finding the pattern or recognizing the pattern. And then what a conjecture is making an educated guess on what's going to come next or what's going to follow in that pattern. And it doesn't necessarily have to be next, it can be. All right, you'll kind of see how it goes. So let's just jump into it. Example 1 says, write a conjecture about the next number in this sequence. And it goes 1, 3, 9, 27, 81. All right, you can kind of see the work that's been done. Well, we got to go figure out what's happening. Obviously, to get from 1 to 3, 3 to 9, 9 to 27, we're multiplying by 3. So you can see that's inductive reasoning. Same thing down here with bases and exponents. You got 3 to the 0, 3 to the first, 3 to the second, and you can tell that exponent's going up by 1. Well, to make a conjecture now is say, hey, what's the next data point going to be, or what are the next data points going to be? Well, if I'm multiplying this top row by 3, I know that I can do 81 times 3 and get my next number or my next value, which is 243. Same thing with my bases and exponents. I know the next base and exponent would be 3 to the 5th. Now, don't overthink this, okay? If you go take your calculator, 3 to the 0 is 1, 3 to the first is 3, 3 squared is 9. The data, it's not going to be stuff that doesn't make sense mathematically. It's going to be very, very sound. All right, example 2 says, write a conjecture about the number of small squares in the next figure. All right, so we got one square, and we can look at this a couple different ways. We can look at the total number of squares. It gives us all the way to, there's 3. It's a 3 by 3, so we got 9 squares there. And you can kind of see what's going on. They're really just adding a square every time. So so I can look at this conjecture, or I can look at these patterns, and to do my conjecture, it's a little bit tough mathematically, because to go from 1 to 4 and 4 to 9, there's not anything that's really solid right there. But you know what the pattern is. Hey, we just added basically another row or another square, which gives us that next row of squares. So I know I'm going to have a 4 by 4. Well, there's your math right there. You've got 4 times 4, which is 4 squared, and you can start to see, you can kind of form a base and exponent conjecture based on that, all right? And obviously for us, it's just 16 squares. And so what I told my kids, I don't really care where you land on this. You need to understand how to get the next set of values, or maybe a few set of values away, based on what they've given you. All right, keep going. Write a conjecture that describes the pattern in each sequence. Use your conjecture to find the next item in the sequence. So we're not going very far down the sequence chain. We're just basically finding the next one, or the one that's missing that happens to come next. All right, here we go. To get from -5 to 10, 10 to -20, 20 or -20 to 40, we multiplied by -2. So it should make sense that to get from 40 to the next number, we multiply by -2. So we by conjecture come up with that is -80. All right, same thing here. You can tell, hey, we're just multiplying by 10. When you multiply by 10, you're adding a 0, so we know the next one, or the next data point, is 10,000. Works with fractions too. Now, don't be tricked here. The number 1, for this instance, common denominator would just be 5 over 5. So then it went 6 over 5, 7 over 5, 8 over 5. We know we got 9/5 is next. We even took it out to the next one. We know the next one would be 10/5, which we would reduce to 2. So looking at data, using inductive reasoning to come up with a conjecture about future points or future data is really pretty simple. All right, so now let's apply it to our geometry. So basically it says, write a conjecture about each value or geometric relationship, and it gives us 3-ordered pair. Now, if this picture weren't here, a little bit tricky to try to understand what to do. Well, let's go graph them. So we went and graphed. We graphed A at -1, -1, B at 2, 2, C at 4, 4, and you can see that all 3 points are collinear. Well, that's something you learned in Chapter 1. So that's writing a conjecture based on stuff you already know from geometry. All right, go to number 5. Angle 1 and angle 2 form a right angle. So I just drew a right angle. I have a ray in there, and I know angle 1 and angle 2 are a right angle. I don't know if they're congruent. I don't know if it's an angle bisector, but what I do know is angle 1 and angle 2 are complementary. Yeah, right. They add up to 90 degrees. So you got a couple different things that you could have put there. All right, let's keep going here. It says angle ABC and angle DBE are vertical angles. Well, you've learned in chapter 1 vertical angles, and we'll get into this even more later on in the book, but we talked about in my class vertical angles are congruent. So I can say angle ABC and angle DBE are congruent. Or I could even just go angle ABC is congruent to angle DBE. Okay, sorry, bad E. All right, pretty simple stuff to do right there. Come to this one, angle E and angle F are right angles, so I drew them up a little bit differently, but we know if you have two right angles, we know that they're supplementary. You could talk about they form a linear pair. You could, there's so many things you could do. Add up, they equal 180. All right, so it's stuff that's pretty simple. It's taking the stuff you've learned and now kind of predicting what else you know about that data or that problem, whatever it is. All right, now back, we get to this thing called counterexamples, okay? So what counterexamples are would be an example that shows something isn't true. Now, here's where this gets tricky in math to me. In math, especially geometry, we usually show where things are right or why they work. This is going to be the opposite. We're trying to find instances where something doesn't work. So I've got two drawings up here, one the book gave and one I made, and it says this. And by the way, we're trying to find a counterexample here. It says if segment AB is congruent to segment BC, then B is the midpoint of AC. That's saying for this part to be true, then this part has to be true. If it's not, then we come up with a counterexample to show that. So I drew it up as true right here. I said, okay, well, I can draw AB and BC being congruent, and B is the midpoint. That's exactly what happens here, and that's fine. But is that the case all the time? Well, no, look at the one the book did, and I kind of connected this line. Let me erase that. Well, A to B is 3 and B to C is 3, but B is not the midpoint. In fact, A and C aren't even connected by a straight line. But if you drew line or if you drew segment AC, you can see that B is not the midpoint of that line. So that would be a counterexample. This would be our answer there. Give an example that shows that this if-then statement's not always true. All right, here we go. Same thing. Jumping out of these four. Determine whether each conjecture is true or false and give a counterexample for any false conjecture. All right, here we go. If A, B, and C are collinear, then AB plus BC equals AC. It's easy to go draw that and make it true. Here you go. AB plus BC is AC. We're good. Well, can I draw those 3 points collinear and them not be, little part plus little part equals whole part? Yeah, look at my answer. I just put C between A and B. They're still collinear, but now AB plus BC does not equal AC. In fact, it doesn't make sense at all. And so there's a counterexample. And so we put a box around it and call it a day. All right, here we go. If angle R and angle S are supplementary, okay, and angle R and angle T are supplementary, then T and S have to be congruent. Well, here's what I know. If R and another angle equal 180, and the same R and a different angle equal 180, then angle S has to be congruent to angle T. I mean, angle R is angle R. It's the same thing, all right? So when this happens, if angle R was 100, well, angle S would have to be 80. Well, if angle R was 100, angle T would also have to be 80. For it to meet the stipulations of the problem, T and S have to be congruent. So I'm just going to go write that that's true. All right, come down here, number 3. If angle ABC and angle DEF are supplementary, then angle ABC and angle DEF form a linear pair. Now, you can draw it as a linear pair, and you see it gets a little bit weird, right? Because I went ABC and DEF. You can see I've got kind of 2 points at the vertex, so looks a little funny. But remember, to form a linear pair, they're going to add up to be 180, but they have to have a shared side. Well, if I just split those up, ABC and DEF, it's the same angles as here. So if you can kind of imagine, I put those congruent. I'm saying that it's a linear pair. I'm not marking these congruent, okay? But that this plus this over here equals 180. Could we have that? Sure. All right. But that is by definition not a linear pair. They're not sharing a side right there. Okay. And so there's an example of that happening. That would be a counterexample. All right, here we go. We've got segment DE, and I drew it and then continued it. It's perpendicular to segment EF, and I can just kind of continue it so you can see it. If it's perpendicular, then I know right here that's got to be 90 degrees. Since this is my shared letter, I know that's my vertex. So this says then DEF is a right angle. Yeah, it has to be. That has to be true. There's no other way about it. You got to pay attention to your letters, okay? For my kids, you got 2-1 skills is open in Canvas, just like any time. And if somebody else is watching this in some other class, you can email me or email your teachers and get any extra help or anything you're needing. Thank you.